welcome back everyone. I'm glad you all returned after the first week. This week, what we're going to talk about is how it is that we form a neutron star. That's where I hope to get to throughout the slides that I'm going to show you today. Each step I'm hopefully going to convince you how it is that we turn a star. For a neutron star, it has to be a massive star, but I'm going to try and explain to you how it is that we end up with a big heavy ball of neutrons, which is what I told you we had yesterday, or last week. So, to remind you again, this is a website where people should go, and I will be sure to have that written on next week's handout. All right. So, first we're going to start off very quickly explaining that stars form in regions containing dense clouds of gas and dust. And I think an important thing for people to understand is that typically stars form all together in a group. It's not like you have a tiny little pocket of dust that collapses on itself and makes a star. Typically you have a very big blob of dust, and many, many stars form out of that blob. And one thing which I don't expressly say in the lecture, but is something you should know about, is that the massive stars, they live sort of fast and furious. They are born massive and they die very young because their fuel burns up very quickly because of the processes that collapsed in the star. So our sun, which lives about 10 billion years, lives about 100 times or 50 times longer than a star that's 10 times more massive. 10 times more massive star will just burn through its fuel much faster. So if you look at a population of old stars, if you look at a place that a dense clump of gas, something like this, which is forming stars now, but if you look at one of these at a much later period in time, what you'll find is that all the massive stars are gone. They are all burned up and die. But some of the supernova explosions that happen at the end of the massive, that I'm going to talk about, some of these supernova explosions from these massive stars actually help the other collection of stars to get going. And that's part of the sort of melange of material you need to make stars form in a group. That is, you need dense gas and dust, and they're falling in gravitationally, and then some of the early stars get going, and then they explode, and part of that explosive material actually helps the other guys get that little kick and start to become a star. So what happens when a star is born is that the material collapses in gravitationally and heats up enough that the fusion reaction starts. And when the fusion reaction starts, it is able to provide outward pressure to the gravity, and then you get a stable system where gravity pulls it in and radiation pressure is pushing it out. And a star that starts to behave this way, or a protostar that then starts to behave this way, is called a star in the main sequence. So this is just a picture of our sun. And so what I tried to explain is that what's happening in the sun and in every main sequence star we know of is that gravity is pushing inwards, and outwards is what's called radiative pressure pushing outwards. And they're in a balance. And so the question we would ask is, so this is called hydrostatic equilibrium. That's just a fancy physics term for that, for the fact that these two things are balancing out. And so what energy source powers this radiative pressure? This is not something that people typically talk about, so as I said, it's nuclear fusion. So what's happening in the sun is a reaction that turns two hydrogen nuclei, which is just two protons, and after enough temperature from the gravitational pull in that heats things up, if you give these two protons enough energy by kind of condensing them down, then eventually the two protons are going to bind together. And then very, very quickly, they don't like to be bound together. What will happen is this proton will decay into a neutron. And in this decay process, what happens is a positron comes out, a little bit of energy comes out, and a particle called a neutrino comes out. So what's happened in this step that turns this proton into a neutron is that energy has come out, but everything else is conserved. The mass difference between the proton and the neutron, in terms of E equals mc squared, there is a mass difference there, and that mass difference comes out as the energy, and then the charge from the proton is transferred to this electron, and the neutron has no charge. So everything is conserved. Charge is conserved, energy is conserved, and so by doing this, by turning the hydrogen into this hydrogen isotope, which has a proton and a neutron, we get some energy. Now, this is still in this bath of hydrogen that's very hot. So what will happen is this deuteron will now just capture another proton, and some energy comes out from that step too. Now, this is happening with our two protons that started off here, and then a second proton joined the mix. If that's happening again somewhere else, next door, you have these two helium-3 products. That's the isotope of helium that has two protons and only one neutron. And if you get two helium-3s next door to each other, they will then join together and create a nice helium atom, which is two protons and two neutrons. And two spare protons come back out. So you started off with 1, 2, 3, 4, 5, 6 protons. You end up with one helium nucleus and two spare protons. And in each one of these steps, you get energy out. This is the fusion reaction happening right here. You take two things, you put them together to make something heavier, and you get some energy out. And that energy helps sustain the reaction. That is, part of this energy is actually the energy that helps kick these guys into these places in the first place. And so for a reaction like this, you get 26 MeV of radiation outwards, and this is your radiation pressure. And this is what's happening in the sun today. And so what we've done, nuclear fusion has done inside a star, has taken hydrogen and made a helium. Energy has come out. This energy sustains the collapse of the star, and it's also the energy that we feel falling on our face when we're lying in the sun. So, in slightly more detail, but not so important, what's happening here in the core is you have hydrogen fusion, and then we have a place in the sun called the radiative zone, and this is a zone where the sort of energy transport is in radiation. So the energy that comes in here, the energy that's formed in the core comes out of this zone and it moves around in terms of photons. Then outside that zone you have the convective zone, and in this zone the energy isn't transported in terms of photons, it's transported in terms of actual motion of the material itself. So this is more like what's happening when you boil a pan of water on the stove. So you can imagine this as being the heat source, and then you have hydrogen up here, and this is kind of bubbling away. And this bubbling away process of kind of the hot material that's here that sort of comes up, gets sort of convected upwards, and then you end up with these sort of convection currents and so on. What happens in here is a great deal of twisting and motion and turbulence. And it is what happens in this zone that then leads to what we see out here, which is things like coronal mass ejections, sunspots, and the sort of magnetic behavior that we see on the surface of the sun. That magnetic behavior is actually driven by this sort of turbulent mess that's happening underneath. Now what's next? So the core of the sun has been fusing hydrogen into helium for the last 4.6 billion years, and we have about that much fuel left. We have another 5.5 billion years of hydrogen left to go. So the sun is halfway through its time burning hydrogen, and we won't be around to see what happens afterwards. But we have a great population of stars out there that, as astronomy and astrophysics community, we have been observing for hundreds of years. And so we have seen stars that are in different stages in their evolution, and so we know how the story goes. So without hydrogen, so after you've burned all your hydrogen, okay, gravitational pressure overcomes the radiation pressure, and it squeezes you in. It increases the density, it decreases the volume, and it increases the temperature. And so what you end up with in something like the sun, So all the helium that was created, so remember we were turning hydrogen into helium, all that helium is collected in the core. And the sort of outer layer of the core, people call this a shell. I might have referred to this as a shell in that flyer. This is like a shell region here where hydrogen is still fusing. And then you have the same layers, as I said before. You have the radiative zone and convective zone and so on. But this outward pressure, this outward increase of pressure that comes from this hydrogen burning in the shell, this puffs up the outer layers of the star. So the outer layers of the star around the core feel this increased outward pressure from the burning in the shell, and so it puffs the star up to become something called a red giant. And so this is just a cartoon of what we think a red giant, when the sun gets to its red giant phase, how it will look. So this is the sun right now, and the size of the star itself will actually extend beyond the orbit of Mercury. And there is some uncertainty about exactly how big the red giant in the sun would be. And it's possible that even the orbit of the Earth would intercept the actual matter from the star. So the outward layers of the sun will be blown outwards by the energy released from the hydrogen shell burning. For the sun, the diameter will increase about a factor of 100. And because you are sort of distributing the energy of the sun out over a larger surface area, actually the surface area is colder in this case. And so the temperature will drop from about 5,000 Kelvin to about half that. And so what happens, when you drop temperature, you actually make things redder. So in the sort of thermal spectrum, red is actually the colder side of the spectrum, and blue is the hotter side. And so that's why these things are called red giants. They have cooler surfaces, so they're redder, and they have huge diameters, so they're giant. And because of this combination of getting big and getting red, they appear very luminous. So they appear very bright. But anyway, when we're in the red giant phase, and we have the hydrogen shell burning, what will happen next? Eventually the temperature will get increased enough, the compression from gravity will compress enough that what will start to happen is helium begins to fuse. So now, rather than turning the hydrogens into heliums, now we have heliums combining together to make heavier elements, carbon and so on, carbon and oxygen. So we have helium fusion happening here, hydrogen fusion happening still in the shell outside, the radiative zone and the convective zone. And the combined outward pressure from these two types of fusion happening in the sun, now we get a lot of outward pressure. So, what happened to being exhausted in the core? Oh yeah. Yep. So then the core, I interrupted my narrative. I forgot about an extra step. What will happen before we get the massive increase in outward pressure is that we will have turned all the helium into carbon. Then we will have a helium shell burning and a hydrogen shell burning. And this arrangement creates a huge amount of outward pressure. And this more or less blows the star completely away. So the outward layers of the star, rather than, as in the previous case, were just puffed up and you still had a star, but you had a puffy red giant, now you completely discard the outer layers. And you get something pretty beautiful called a planetary nebula. So this is a picture from the Hubble website, I believe, a few pictures I grabbed from the Hubble website of what is called planetary nebula. Now, this word planetary nebula is not to be confused with anything to do with planets. And this is a sort of a mistake of history that astronomers, when they first had primitive telescopes and pointed them and saw these sort of fuzzy objects, they confused them with planets. And so they got the name planetary nebula, and unfortunately, nobody has corrected it since. So this has got nothing to do with planet formation or anything like that. It's just a name left over from a mischaracterization. And so what you see in these planetary nebula is you see the outer layers of what was a star has now been blown off into this nebula region. And we will have a star, the core of the star left in the center. And you'll see in these images that they have been colored in different colors. And these colors correspond to the light emitted by different elements. So we can actually look at these diagrams and tell, oh, we got, you know, a helium rim on the outside and a hydrogen bit in the middle, and maybe some of the other lighter elements that are in these stars. And so we can actually sort of map the kind of structure that I showed you of the different elements burning. You can sort of map that in this sort of blown out nebula. And these things don't last very long. This arrangement only has you know, enough sort of energy left to have these glowing for a few thousand years. So these are pretty short-lived arrangements of the system that you get this time-burning nebula. What happens to the core? So we've blown off the outer layers. We had a carbon core. We had helium and hydrogen burning in thin shells around the core. So the helium fusion reaction, in order to turn helium into carbon, you need temperatures up in the center about 20 million Kelvin. If you want to turn the carbon that you created into heavier elements, if you want to combine the carbon and oxygen into heavier elements, if you want to get fusion of carbon, you need temperatures about 1 billion Kelvin. So if the temperature increased following the contraction after the helium phase, after you burn the helium and you kind of, your outward pressure in the core decreases because of the fusion in the core is slowing down, it compresses the thing, and if you can't compress it sufficiently to heat it up to 1 billion Kelvin, then you can't fuse the carbon. So gravity continues to collapse the core, until quantum mechanics comes to the rescue. Okay. So before, the outward force was provided by this nuclear fusion. However, if you can't get the temperature up, you can't fuse carbon, you've got no more outward pressure, gravity pushes you in, and something is going to stop the gravity pushing you in, and that's what we're going to talk about now. So quantum mechanics comes to the rescue. So before I describe exactly what this quantum mechanical force is, I just picked out the definition of quantum from the Webster Dictionary. And so when people think about quantum physics, sometimes they think about, oh, it's weird, it's cool, it's, you know, it's got stuff that's happening and not happening at the same time, and they have these associations of Schrodinger's cat and dead and alive and probabilities and all that. What quantum is really about is quantization. That stuff is quantized. When you think of quantum physics, the first thing you think of is that all that weird being dead and alive at the same time when it's not observed, all those weird phenomena arise from the fact that the system is quantized. And so any of the very small increments or parcels into which many forms of energy are subdivided. So quantum physics arises from the fact that at the smallest level, things come in units. And those units can be subdivided. They come in quanta that cannot be broken down into something smaller. And this is you know, the classical example of this sort of quantum behavior is looking at the hydrogen atom, where you just have a proton and an electron. And if you look at the emission that comes from this, you see very specific lines. So this is the hydrogen emission spectrum. And so this tells you that this was like one of the first pieces of strong evidence that tell you that the electron can't live anywhere at once. It can't live in any particular orbit and move from one orbit to the next and emit a whole spectrum. It emits from very discrete orbits and emits a very discrete spectrum. So when you want to understand or want to start to think about quantum physics, the first thing you have to think about is when stuff gets very small, stuff gets divided into very discrete units. Now, some very famous physicists here, who I'm sure you all know about. So the technical term for electrons, is that they're fermions, and then named after Enrico Fermi. And fermions obey something called the Pauli exclusion principle. And this is partly the reason why things are quantized. Is that what it says is that two identical fermions cannot occupy the same quantum state. So if I am a fermion, if I'm an electron and I'm sitting in my state, and you're a neighboring guy over there, you can't approach me. You have to stay at a particular distance in your quantum state, and there's no gap in between. You can't sort of incrementally get closer to me. You're just bound out there. I have to move out of the way completely over to another quantum state in order for someone to move in. And so you can sort of see where I'm leading you now. We're crushing something down. We're going to start bumping up against this quantization, it's called degeneracy pressure. And don't worry about why it's called that, but that's what it's called. And that is the pressure of not being able to move into any other state. There's no states available. Everything has been, the whole bus has been filled up, all the seats are taken, and nobody else can get in that bus. And so densely packed electrons cannot disobey the Pauli exclusion principle. And this is called quantum mechanical pressure, called electron degeneracy pressure. So earlier on, people were coming up to me, or not earlier on, but last week people were coming up to me because I put out this term. And I deliberately didn't explain it because I was going to explain it all today. But people thought the word degeneracy meant that somehow they were decaying or they were dying or there was some end of the neutron or end of the electron, and that somehow was, that ending of the particle was somehow providing an outward force. They are not ending or dying or going anywhere. They're just stuck in the tightest possible quantum mechanical arrangement that nature will allow. All right, where are we at? So what we have now, if you follow the story, is that we have this carbon core that can fuse, and the electrons that are in this core, they can't get more densely packed, so they provide the outward pressure. You have maybe some helium and hydrogen burning in the shell, and the rest of the star has been blown off into this planetary nebula that only lives for a few thousand years and then goes away. And so if you try and find these guys, you maybe can't even see them, but there's white circles that are circling them in this image, these tiny little dots. These tiny little dots are white dwarfs. That's what they're called white dwarfs. This is how it came to be, that we ended up with these very tiny stars. And this is the fate of main sequence stars which start off with a mass of less than 8 solar masses. And so this is how it's going to go for our sun. The story I told you. And so if we happen to be around in 6 billion years, what will first happen is that the sun will enter the red giant phase. And like I said, the red giant phase might even intersect the orbit of the Earth. So basically everything, by the time the red giant phase happens to the sun, everything on the Earth will be completely cooked. We will not be around to see the sun turn into a white dwarf. Now, what about the big guys? What about the stars that have masses greater than 8 solar masses? So this was the story that we had with the smaller fellows. However, they do have a gravitational mass so great that the gravitational pressure pushes the core temperature above 1 billion Kelvin, and fusion in the core continues. And so the sort of reactions we see when you allow now carbon to combine to make heavier elements, the type of reactions we see, and this is just a very, very small list, and you don't need to pay attention to that so much, except that you can burn, if you have some carbon and helium together, you can easily get oxygen plus energy. So each one of these gammas is to symbolize that energy also comes out. We bind the things into a heavier atom, and we also get energy out. And so this is how oxygen, magnesium, sulfur, silicon, and argon, all these elements are all formed in this fusion process. And what I want you to think about, what's happening is that this is all happening in successive layers. The heavier elements are in the hottest zone, fusing into heavier and heavier elements. And as you move away from the core and the temperature cools slightly as you go away from the core, then you have different shells. So you have the heaviest elements fusing in the center and successively lighter elements fusing in successive shells outward. And the sort of elements that stars make in this process is all of these elements that I have listed in the red box here. And there's also a little bit of nickel, which is this guy here. And so something happens. Something happens when we hit iron. So earlier on in the case of the massive star, or sorry, in the case of the smaller star, something happened when we hit carbon. That thing that happened was that we just didn't have enough heat in the core to get the next reaction going. Something similar happens when we hit iron, and this is maybe too technical to talk about, but I'll just, for those who are interested in this kind of thing, this is what's called the binding energy curve. And it basically tells you how much energy you can get out if you glue things together. And so if you go from a hydrogen and you make a helium-3, you can get out the difference between these two levels. So you can go from up to 2.5 MeV. So that's what you get out of the system. If you go from helium-3 up to lithium, you can get probably another 2.5. And as you can see, the amount of energy that you can get out of each step as you go up this side of the curve gets smaller and smaller and smaller. And eventually you hit iron, which is at the top. And iron has a special, remarkable property that it is right at the dividing line here between getting energy out. And so what this dividing line tells you is that if you live on this side of the line, you can join two things together and get energy out. If you live on this side of the line, you can pull things apart and get energy out. And so this is the line that divides places where you can have a nuclear fusion reaction from places where you have a nuclear fission reaction. So all the heavy stuff you know about uranium and all the stuff you hear about in nuclear reactors, that is all heavy and it lives on this side of the curve. And that, when you live on that side of the curve, it means you pull stuff apart and energy comes out. If you live on the other side of the curve, you put stuff together and energy comes out. And so when a star makes iron, it stays as a fusion reactor. It's over. No more energy can come out of this reaction. So, if you're now we're in familiar territory now. No longer we can sustain a fusion reaction. Either the temperature isn't high enough, or in this case we have iron, and with iron you can do nothing. By the way, this is why iron is so, one of the reasons why iron is so abundant in the universe, is because in these massive stars, at the end of the day, everything ends up in iron and it can't go any higher, so you're sort of stuck with it. So because it's the sort of end product of fusion, that's one of the reasons why iron and nickel are very common elements, because those are the elements at the top of the binding energy curve. So, once again, quantum mechanics comes to the rescue. But before that happens, before the quantum mechanics that I kind of described, this degeneracy pressure kicks in, a few reactions start to happen in the core, in the iron core. So what happens is something called proto-disintegration of iron. So all the hard work that the star did, binding smaller elements up into the heavier ones and building bigger and bigger atomic nuclei, that all gets undone very quickly. The temperature is so great, the energy sources from the collapse are so great that it smacks the iron nucleus apart, and you end up with 13 helium nucleuses come out and 4 spare neutrons. Very quickly, very, very quickly, the pressure gets so great that the electrons that happen to be in the neighborhood of the core, these electrons get pushed on top of the protons. This is the protons, sorry, the helium after the 13 heliums and the 4 neutrons are created, then the helium actually breaks apart, making its constituent nucleons, that's the 2 neutrons and the 2 protons, and then electrons that are nearby glom onto the protons and turn them into neutrons, and they spit out neutrinos. And so you started off with an iron nucleus, and now you've ended up with the number of nucleons. Every nucleon in there has turned into a proton, has turned into a neutron, and neutrinos. So this is how you get your big ball of neutrons. And now, gravity comes in again. He's relentless. He keeps pushing. And eventually the neutrons end up the same way the electrons ended up in the core of the white dwarf. They end up so close together that there's no states for them to live into. Neutron degeneracy pressure. This is the same situation with the electrons. Now the neutrons are saying, you can't come any closer to me because I'm a fermion. I obey the Pauli exclusion principle. You obey the Pauli exclusion principle. You stay over there, I'll stay here. And so basically, the inter-neutron distance is as small as it can possibly be. And so you end up with the most densely packed arrangement of neutrons you can get, and gravity can't push it any further in. Hello? I missed a nice transition. So, I had a very cool switcheroo there. There we go. All my blue arrows, which are supposed to be the collapsing force, all suddenly bounce off the big ball of neutrons. Oh, come on. There we go. They bounce off. And so the collapsing material that was collapsing down onto the neutron star, so onto the ball of neutrons and compressing the neutrons and compressing them, eventually when the neutrons are reach this neutron degeneracy pressure state, they can't be compressed anymore. And the outer layers around the core that were compressing it down, they bounce off and they bounce out and make a supernova. Now, probably we shouldn't do this.
And the neutrinos are part of the energy that...
Absolutely. We have a very well-read person here. The neutrinos cannot be forgotten at all. They are a huge explanation for where the energy comes. Now, probably shouldn't do this because it's probably lame. But, well, we tested it at home yesterday, and it didn't look so great. But, you know, if you want to look at this on YouTube, there's people who do a great job with it. And so, to help you to help visualize the outer layers sort of collapsing as the neutron surface of the neutron star collapses, and eventually the neutron surface stops because it can't go anywhere, and the outer layers bounce off. That sort of happens if you have the two balls of different masses. Now, this is a terrible football that I own, and a very old tennis ball. So I just want you to to understand how badly this ball bounces of it by itself. So this is this is not the best, and this also is. But if you have an arrangement where, so now I want you to imagine that this is the outer layer of the neutron star surface that's collapsing. This is some molecule of oxygen, or atom of oxygen or whatever that lives in the shell beside, and it is being pulled by gravity down on top of this, crushing it in, and then, here we go. Low gravity and all its wonder. So let's just do it one more time. It's worth seeing again. All right. Now, what's up first? No, that's too bad. There we are. Brilliant. And as my friend in the front row here pointed out as well, you get all these neutrinos coming out. So this reaction where the electrons bind to the protons, turn them into neutrons, and spit out neutrinos, this is like a mega blast of neutrinos. But neutrinos are they don't like to interact. I don't know how much people have talked about neutrinos to you in the past. Maybe I should have spent some time discussing that. But neutrinos are whizzing through us right now. If you want to detect a neutrino, you really need to be lucky. They don't like to impart their energy. They don't like to collide with stuff, to interact with stuff. They only can use the weak force, which is, I don't know if people have told you about the different forces. You have the strong force like that is propagated by gluons. The electromagnetic force, there's also a force called the weak force. And the weak force is called the weak force for a reason. It just doesn't like to mediate. And so even though an enormous amount of energy is in these neutrinos, it's not easy for the neutrinos to give the energy to material that's around it to push it out. But it still gives it some. So you have sort of two things that are happening, which is the fabulous double bouncing ball where the outer layers bounce off. So you have sort of a kinetic energy kick type of situation. You also have the neutrinos blasting out as well. And so all of this leads to what's called a core collapse supernova. So this is a slide I showed last week for those who were there. This is again just a summary of everything imploding, then the supernova shockwave bounces outwards. And so this is very famous supernova, Cassiopeia A. This is a composite image with X-rays and infrared and optical radiation. And people who are at the front maybe, or who have laser vision, will see that there's a tiny sort of cyan speck in the middle. This is the neutron star at the center of Cassiopeia A. And somebody last week was asking me a question about neutron stars and can we see them, and is it only that we see them because they're in the beam? And I kind of told them, nah, we don't really see them. Like, we see them in the case where I discussed last week where we had a binary, and the binary can dump material on a neutron star. And we see them, and we're going to talk all next week about how the radiation from the pulsar comes out. But also, in a case where something like Cassiopeia A, which is only about 300 years old, the neutron star itself is still hot enough that it emits thermal radiation. So this is a relatively young neutron star, and so if you have the right kind of X-ray telescope and you can point it at it, you can see thermal X-rays. Now, the neutron star that's at the center of Cassiopeia A, we don't see it as a pulsar. So that could mean that the beams are not pointing at us. It could mean that it has, for whatever particular reason, it doesn't have the strong enough magnetic field. So there is some. Nobody is throwing away the theories. There are scenarios. Maybe the spin is a bit too slow, and if the spin is over 4 or 5 seconds, there are reasons why the pulsar mechanism kind of won't turn on. But the narrative that I've told you about, the core turning to iron and then into neutrons and being compressed, that is still absolutely consistent with the picture that we see here in Cassiopeia A. Oh my God. All right. This is G11.2 minus 3, also called SN 386. This is the same image I showed you again. This is the X-ray pulsar here at the center and the supernova remnant outside. This is about, Cassiopeia and this guy are equivalent, 3.5 kiloparsecs or 11,000 light years away. And this is about 16,000 light years away. And here's another case here, RCW 10.3. And so, these are the remnants of massive stars. This is the outer, and again, in the same way that we look at the planetary nebula, and they told you that the different colors in the planetary nebula correspond to the different elements that were in different shells of the star. The same work is done in the supernova remnants. We can see the different atomic elements radiating in their particular colors in different parts of the shell, and it totally reinforces our understanding of this shell burning, that the heavier stuff is fusing in the center and the lighter stuff is fusing in higher shells, which makes complete sense.
How big in light years that ball is?
Pardon me?
How big in light years the diameter?
Oh, I can maybe try answer that next week. I don't have that off the top of my head.
Well, it could be.
And just to complete the tale, but this is not part of the lecture series, and I don't really know much beyond this. But if you have a big enough star, 20 solar masses, 15 solar masses, in this collapse of the neutrons, you do collapse enough neutrons into a density that you pass what's called the Schwarzschild radius, which is the radius necessary for you to have a black hole. That is that the escape velocity from something that dense and heavy is the speed of light. And so this is how you form this is how one of the processes for forming a black hole. So, well, I maybe shouldn't show that, but I want to just recap. If you're a small star, maybe 5-8 solar masses, the end of your life is a degenerate carbon core balanced by neutron degeneracy pressure, and that's called a white dwarf. If you're between 8 and 15, 8 and 20, then you have enough matter and enough energy in your collapse that you can fuse all the way up to iron. Then the iron turns to neutrons, neutrinos come out, and you end up with a neutron star. And then you have higher mass than that, 15, 20, 30 solar masses. The neutrons get compressed into a density that like sort of, the gravitational force then eventually wins and you end up with a black hole. So what's the evidence? So I've told you, look, wonderful story, and I'm going to try and present some of the evidence. And you might find the evidence not so, how should I put it? It's my fault because if you want to really understand all the stuff that I've shown you, you need to take like an undergraduate course in stellar evolution. I'm trying to do stellar evolution in 45 minutes. So some of this might seem so nice, but you have to understand that there's a huge body of literature, and all of these individual pieces from the body of literature all fit this unified picture. So I'm just going to pick a couple of what I think are the most accessible elements and try and demonstrate them for you. So that you believe this stuff I've told you. So I told you what's happening is fusion reaction turning the protons into helium. So we have detectors. This one is called Borexino. It's in the Gran Sasso mine in Italy, and this one is called the Sudbury Neutrino Observatory, and it's in Sudbury in Canada. And these are big, huge tanks of water, or sometimes a material called scintillator. And this is a material that if one of these neutrinos that's passing through us all the time, if it just happens to glance one of the atoms in that material, it makes a signal. And so we have successfully monitored the neutrino emission from the core. So I remember I told you that what we see from the core is coming from what we see from the sun in visual radiation is coming from the photosphere, the region at the edge. All the action that I've been telling you about is happening in the core. How do we know what's happening in the core? So the only thing that gets out of the core is the neutrinos. All the other stuff that's created in the core all gets stuck in the radiative zone and in the convective zone. So the only real probe we have of the core is the neutrinos, and we have measured the neutrinos from the sun, and it all fits. So this chain of fusion to make helium, this is only one, and the energy that these neutrinos come out, this is only one chain. There's like a dozen other reactions that can happen, making neutrinos with slightly different energies, and we can measure them all pretty precisely now, in the last 20 years. And so the fusion situation in the sun is done. Now, alright, this is, maybe some of you are familiar with this. This is something called the HR diagram. And what you have is sort of color on the x-axis. So stuff that's over here is red, stuff that's over here is blue. On this axis you have the dim stuff up down here and the bright stuff up here. And kind of this way you have radius. So there's the very wide fat guys are up here and the very skinny small guys are down here. Now this is a particular, so this is all the stars in something called M3, which is a globular cluster. It's old. All the massive stars are all long exploded. This is a lot of pulsars or these globular pulsars have a lot of pulsars in them because all the massive stars turn to neutron stars, and then most of the neutron stars have pulsars. And so, for instance, the fastest pulsar I told you about last week, the one that spins at 714 times a second, that is found in not this globular cluster, but another globular cluster. But so all these stars are old. All the heavy ones have exploded. And so when you look at them on this diagram, they make this pattern. When you look at them, when you look at their color versus their brightness, they live in this particular shape. They're not just everywhere. It's not like any color and any brightness. There seems to be a very specific place where all the objects live. And so these guys are the main sequence guys. These are burning hydrogen. This is called the red giant branch. This is when you're hydrogen burning in the shell and have helium in your core. This is called the horizontal branch. These have helium burning in their core. And the white dwarfs would all be down here, which is they're blue and small. And maybe this is an unsavory thing for me just to say, to plump this image and tell you the story again. But you have to, when you see nature do something like this, when you point at stars and just say, we're going to plot the colors against the brightness and see what we get, and we see a very specific shape, not a random shape, there has to be an explanation for that. And the explanation for that is exactly what the story I told you, that the different shells burn, and they puff up, and they make them redder, and then they compress down, and they get bluer and smaller. That's the explanation. So the story I told you is born out in a plot like this. And you could read 10 books on this subject to sort of fill in all the bits that I've left out. The other piece of evidence I'm going to demonstrate, this is getting close to the end now, is a core collapse supernova called 1987A. And this happened in the Large Magellanic Cloud. So this is a photo taken in Chile at the ESO, European Southern Observatory. This is our galaxy, the Milky Way. This is the Large Magellanic Cloud, which is like a little galaxy nearby. And then this is the Small Magellanic Cloud. And not in our galaxy, but in the Large Magellanic Cloud in 1987, a supernova went off. This is a picture of a supernova. This is only a baby, 28 years old. And we have been watching this for the last 30 years, and we can see the sort of, I probably should have brought a movie. There's a little movie of kind of the progression over 20 years of the outward shell breaking out. So this is the most nearby core collapse supernova we have had since we've had neutrino detectors. And so remember we talked about how the electrons get forced into the protons and neutrinos come out. Well, at the same time this fellow went off, a neutrino detector, it wasn't actually used for neutrino detection, it was used for proton decay experiments. They had a big basin of water, and that big basin of water is full of protons, and they were just staring at it all day and all night, hoping to see a proton decay. If we saw a proton decay, which we had never seen, but if we did see a proton decay, that would tell us that the ultimate fate of the universe, because when all the protons are gone, it's all over. But we've never seen a proton decay. But anyway, this same big tank of water with all these, so you probably can't see, it's a big tank of water. This is a man in a boat, and he is instrumenting some of the electronics. The electronics that are around are these, what are called photomultiplier tubes, very, very huge lights, sensors, and so they are hoping to see a proton decay, and that proton will give a little bit of energy and a little spark will come out and they'll see it. But what do they see? They just one day, in 1987, they're going along, and this is a sort of time in seconds, and this is a sort of ambient level of so cosmic rays and other stuff go through here and create a signal. So you have sort of an ambient cosmic ray signal that's happening. That's, by the way, why all these things are in mines, to try and shield you as much from the cosmic rays, but still a few cosmic rays get through. And so you always have some level of cosmic rays, and then at some point it's like, whoa, a huge signal all at once. exactly at the same time that astronomers noticed, oh, something's gone off in a large magellanic cloud. So this is the neutrinos from this neutrino creation part of the implosion. And so those are the three pieces of evidence that I will provide you as best I can to try and justify the narrative I've told you of how it is that we get a neutron star. And so that's where I'm going to leave it today. So thank you very much. All right. So let's. Who wants it? Go ahead.
You said that things sort of stop at iron.
Correct.
What about the rest of the elements?
What about the rest of the elements? Okay, that's a great question. It's a wonderful question. So, when I said things stop at iron, what that means is that iron can sustain a fusion reaction. If you try to put stuff together with iron, you can do it. You just can't get energy out. You have to put energy in. So the elements higher than iron come, we believe, from the explosive force itself. So you have now all the other elements that are all the elements lighter than iron and iron in the sort of shell of a star. And then the explosion comes off, and all the neutrinos come out, and all the impulsive energy comes out. And this energy isn't trying to sustain a reaction. This doesn't have to be sustainable. This is sort of an energy dump exercise. It doesn't have to be, it's not trying to sustain itself. And so the energy that's dumped into the outer layers of the supernova during the explosion, that is able to fuse elements heavier than iron and make the other elements. So the elements that are heavier than iron are made in the explosion itself. And for that, we don't need a reaction. We don't need to keep doing that. We don't need energy to come out like we do with the lower elements. And so that is what we believe is the source of all the elements that we know about. All the heavy elements that we know about were all formed in successive explosions. So what I told you earlier on, at the start, I said something like this, that stars are all born in the same blob of gas, and the heavy ones live fast and die young. They explode, and they shoot the heavy elements they've made. They shoot them out in the neighborhood, and then these elements are then in the vicinity and of the other stars that explode. And so through this sort of explosion process, you are able to deposit energy into the heavier elements and make them heavier and fuse them up. So the explanation is that the fusion reaction stops at iron. If you don't need to sustain a reaction, if you're just willing to expend your energy, then you can expend it into making heavier elements. And so yeah, that's where it comes from. There's also other stuff, like, and I think those of you who may have seen Nahi talk about cosmic rays in 2007, Nahi would have covered with you how it is that cosmic rays can also undergo nuclear reactions. They can undergo decays and also other collision interactions and sort of fill out all the isotopes and all the other elements that we see. So there is some sort of propagation origin to some of the elements as well.
Can you explain that?
I'm sorry, I'll come to you next.
Oh, okay.
No, you please, up there, yes. No, you're
Me?
you're
Okay,
the man.
thank you. When you say that two neutrons cannot occupy the same quantum state, what exactly is the state? Is it a physical location? Is it something else?
It is, I mean, the simple answer is it's a combination of your energy and your position, and also other quantum mechanical properties like spin. So there is a thing called spin that fermions have. It's a number that helps us understand this quantum mechanical arrangement. And so there are a few numbers that quantum mechanics uses to describe the arrangement. And it is that you can't have the same. It's like having a phone number. It's like you can't have the same phone number as the first, but you can have one digit different, but not the same one. And so we write down the numbers So okay, we have a position, that's a number. We have the energy, that's a number. We have the spin, that's a number. And then we can arrange that number in different ways, slightly. But that's the state. That maybe isn't a very nice answer, but you kind of have to understand this quantum mechanical arrangements in order to understand precisely what a state is. But the simple answer is it's position and energy and a few other quantities. So you can have the same position and energy with a slightly different spin, and then you can live beside each other.
Right.
Now, you're Matt.
Oh, can you explain if I am correct or mistaken about the other process that you can create or form heavier elements, which is in the red giant's atmosphere by neutron absorption?
You're at the end of my...
When a neutron, because could approach the nucleus and eventually decays into a proton, then you have a new element out of
Yes.
it. So that's another process that
Sure.
heavier elements form. Not necessarily explosion, but neutron absorption.
Yeah.
Is that correct?
So that you can have isotopic decay. So that is, an isotope is an element that has the same number of protons, but then a different number of neutrons. So you might have 5 neutrons and 5 protons, and you might have 5 protons and 6 neutrons. So it has the same atomic charge, but it has a different mass. So stuff that has the same atomic charge but different mass is called an isotope. And so yeah, you can have a neutron decay that turns one into another. And so this is like when you hear about things like polonium-210 and all this enrichment stuff that people are worried about in various parts of the world about people making a bomb and stuff. In order to make a bomb, you need to make these isotopes. And there you need to put energy in centrifuges and all the rest of that to, create the right configuration. So there is other ways that can happen in sort of outer space through these interactions of atmospheres with cosmic rays, or down here on Earth in centrifuges and stuff like that. So I think there are maybe the short answer to your question is yeah, I believe so that there is other ways you can change an element into another, but which is neutron decay. Yeah.
Thank you.
How long does it take for a star to turn itself into a supernova, and what triggers it? Is there a mechanism that triggers it, like a match to start a...
So the answer to the question is, so the question, I'll repeat, is what determines how long it takes?
Yeah.
How does it take so long? So the answer to that is, it depends on the mass. And depending on how much mass you have, that determines how much gravity you have. And the more gravity you have, the more gravity you have to fight. And so you are forced to burn through your stuff faster and faster and faster. So the heavier stars live the shortest, and the least massive stars live the longest. And so our sun, one solar mass, is going to be in the hydrogen burning phase happily in the main sequence for about 10 billion years. If you have something 10 times more massive than that, it lives 100 times less long. So,
But when they explode immediately. They're seen during daytime, and they were not there.
Absolutely. The impulse of energy that is seen in the supernova. I mean, the actual story I told you about how the thing condenses and then the electrons glom onto the protons and turn into the neutrons, that is happening in less than a second. that whole action is happening in less than a second. So yeah, the final crunch that leads to the neutron star happens in incredibly short space.
And
So the Pauli exclusion principle and the neutron bounce, let's call it. I mean, the bounce from the neutron core.
Yeah.
Okay. So in a classical situation with two balls,
Yeah.
the model that we think of to explain it is that there's an elasticity in the core, and you don't have an elasticity in the neutron core of the same kind. And so I'd like to maybe put one or two questions together out of that. So
yeah, I actually think I know. I actually think I know where you're going, and you're very perceptive. This is a very perceptive question. And so his question is, the story I told you with the ball bouncing, that what happens, where the energy comes from the upward going little ball, is that the larger ball sort of compresses, and that compression is, is then released, and that release actually imparts energy outwards to the lighter ball, and that's why it goes off. And so his question is that what is happening in the neutron star? Is there like a bounce back? And so I don't think there is a bounce back. And the analogy that I gave you is not a true description of what happens. It's not it is a demonstration to sort of give the feel for what's actually happening. But what is actually happening, I understand, is not the same as this simple demonstration that you have a squeezing and then a bounce back. And so, what is it? Most of it is the neutrinos. The neutrinos that get spat out, they're the main guys. They're the main guys applying the outward energy to expel the supernova. Because there's something else that I didn't talk about. And this is still in active area research, by the way. I should say that the precise details of the explosion is not written down 50 years ago. We're still working on it. But there's another complication that I didn't say, which is that the outer layers are coming down, and I said that they kind of bounce off the surface of the neutron star. What are they bouncing into? They're bouncing into their buddies from upstairs who are coming down too. So you actually have a sort of a shock wave of the material that's bouncing off the neutron star and the material that's still falling into the neutron star. And so you actually end up with sort of a weird equilibrium where stuff is falling and stuff is coming back off the neutron star. And in order to get the thing to actually come out and make the supernovas that we see, you need to tap the neutrino energy. So yeah, it's the neutrinos that actually blow the big apart.
does the Schwarzkopf radiation pressure, or whatever you call it, does that overcome the exclusion principle? So you said if it gets below the Schwarzkopf radius, if something gets below that,
yeah.
Does that mean that the neutrons are somehow closer than permitted by the...
I don't know what happens. I don't know what happens. When the arrangement of matter density, when you have an arrangement of matter density that exceeds the conditions to make a black hole, what precisely happens there, I don't know. And I wanted to have an answer. I wanted to have an answer to that question today because I was wondering it myself. Because there's other things that have to be conserved. There's all these conservation laws, and one of them is a baryon number for people who are interested in. So I wondered what happens to the neutrons, because the neutrons are baryons, and we don't believe that baryons are allowed to be magicked away. They're not. Baryon number is something we believe is supposed to be conserved. And so if you make so this is now I'm just talking off the cuff. I genuinely don't know, but I don't know what it is that exactly happens when you have the matter density sufficient to make a black hole. That the matter that's there suddenly turns into a black hole, and that step there I don't know.
There are two types of
No, no.
two types of supernovas,
Mhm.
type 1 and type 2.
Mhm.
What's the difference between
Well, that's the difference. It's a great question. Oh, I love these good questions. So type 2 is what we just described, which is a core collapse supernova that happens in a massive star. Type 1 happens with a white dwarf, we believe, most of the time. And so the story I told you about white dwarfs is that they don't explode, that they have a carbon core and a helium and hydrogen burning shell, and that's the end of it. But more often than not, the star, a single star is not the norm. Like our sun is a star by itself. Most of the time, stars have buddies, binaries, triple systems, and more complicated systems. And so what happens if you have them? So the thing about the white dwarf is that it's incredibly dense. This core is very, very dense. So even though they may not have a huge mass, they have a large density, and that creates a pretty steeply falling potential well. And so the nearby material from a companion star can fall onto the neutrons, fall onto the white dwarf. And so now you have a situation that a star which isn't fusing in the core suddenly is getting mass piled onto it. And so eventually the mass that gets piled onto it from the neighbor pushes the core down. And then you get the supernova, then you get the same sort of, situation. The same situation that you compress things down and they explode out.
Does the fusion actually start? The fusion process starts?
I don't know if the fusion process starts. I think it's just the gravity. Yeah. So I spent a lot of time trying to explain to you how it is that the core collapse supernova happens. The white dwarf gets out of its equilibrium. So it's all about the equilibrium of the outward pressure and the gravitational force. And if you get out of the equilibrium, then you're in trouble. And so in the core collapse supernova, you get out of equilibrium because you can't cause a fusion. You can't continue the fusion with iron. In a white dwarf situation, you get out of equilibrium because you get more mass out of nowhere from your companion. And this is one of the reasons maybe Elise or Tim talked about supernova used as distance markers. And so the reason the supernovas that are used as distance markers for cosmology are the type 1 supernovas, because they're a bit more well-behaved than the massive star collapse. Because the massive star collapse, what actually is the brightness of the supernova really depends on the mass that you started with. Whereas all the type 1s all start with more or less exactly the same mass because they all start with a white dwarf. No, I had this man.
Are neutron cores so tightly held together that they hold their shape without change, or do the cores quiver at all?
Whoa. So the answer is the second one, and this is a very high. This is really in the sort of higher levels side of the story. So there is, I wouldn't say a quivering, but there has to be an ability for the neutrons to reconfigure themselves slightly to respond to the different gravitational stresses that happen. So there are gravitational stresses, and they have to be counteracted by the neutron degeneracy pressure. So the neutron degeneracy pressure, the neutrons sort of will rearrange themselves depending on the minute, well maybe not minute, but the precise gravitational stresses that happen. And so that takes time. So it takes time for a neutron to realize, oh no, the gravity is maybe moved a bit. The situation has moved a bit. We need to slightly reorganize. And so that reaction time happens at the speed of light. The information that a neutron will learn about how something else moves that will travel at the speed of light. And this is important about how the black hole gets formed. If you can't respond quick enough, if the change in the gravitational, so when you form a black hole, what happens is you first form a giant neutron star, and then but the giant neutron star is not the information of the gravitational stresses cannot be responded to quick enough for the neutrons to kind of rearrange themselves and defend against the gravitational force, and that's what we believe makes the black hole happen, is this sort of response time. So that was a kind of a hand-wavy hard question for me to answer because this is the real high-level stuff. But so your question, if I recall, was do they kind of quiver or move around a lot or a bit? Yeah, they do have to move around a bit to respond to changes in the sort of gravitational stresses.
And would that moving around impart a bounce to the material above it?
I don't believe so.
Just curious, why does stable fusion jump from helium to carbon, moving over like lithium, beryllium, boron?
I just didn't go through those chains.
Oh, okay.
Those chains, the end products are all the light elements. I just didn't illustrate those chains, but yeah, there are chains.
In the theater world, you would use red light to create a warm effect, blue for cool.
Yeah.
And I come here and you see
Yeah.
a decrease in temperature equals red. So I'm a little confused.
What was the question? The question was, people are familiar with the concept that blue is cold and red is hot. And now I stand up and tell you, well, actually, the blue is cold, but the blue is warmer than the red. Why is that? So, this is sort of well, okay.
Black body radiation.
Yeah. So when you think about a hot iron, like you're gonna brand a cattle or something like that, and you take a hot iron out of the fire, what we see is like a red glow, and that red glow over the existence of man has associated us with the fact that red is hot. Now, that glowing rod from the fire, if you had the right kind of eyes to properly analyze the colors that were in there, you would see that as it gets hotter, it gets bluer and bluer and bluer. So the idea that white hot is hotter than red hot because you're getting more of the spectrum in there. The red hot stuff is the colder stuff. Once you start getting the green and the bluer colors in there, that means you're moving towards white hot, which means you're moving towards hotter. And eventually it's ultraviolet and beyond there. So the idea that stuff is blue, that comes from the fact that, when you're cold, your lips may be turned blue, and that's a physiological thing. It's not actually to do with the actual heat of something. That's just a physiological response that makes us look blue. Or a lake or whatever looks blue, and you say that's cold, and a fire looks hot. A fire, actually, the hotter the fire gets, the bluer it gets.
Like an acetylene torch. You
Yeah.
light it off, you have a little flame to get the acetylene, you just blues on.
So I don't exactly know what you're describing. So I'm not familiar with this particular torch. And it may be blue, I'm just going out on a limb here. It may be bluer because the particular the particular metal in there, the metal that's in there might have an emission line that's in the blue. So there are other ways to get like hot stuff to be blue, or like fireworks, for example. Fireworks are made of all different materials that have been chosen over hundreds of years that have different light properties when you burn them. And so you can make a blue firework or a red firework or a green firework. And that's more of a line emission from atomic elements. What I'm describing about when you have a hot thing, which is called a black body for historical reasons, but a black body emits in the red when it's cold, and then it gets bluer and bluer and bluer as it gets hot. I'm going to go up above you. Yes, please?
No, somebody behind me.
Why must the universe form pulses? What's the significance of the pulses in the universe? Why must it form?
Why not?
Why does the universe need to form pulses? What is the significance of the pulses in the grand universe? You know.
So I don't know if I can address that question. I don't know if I can get on board with the idea that the universe needs to create pulsars. It just so happens that nature has a kind of a how would I say it? Well, it's like the laws of nature manage to arrange themselves in reactions, and these reactions, lead to a lot of phenomena that we're familiar with. It's just the way nature manages to arrange itself. And so the story I've told you today, I know it's a complicated one that people are not familiar with, but yeah, nature just, for instance, there is no reason that I know of, like no underlying reason, and maybe I'm wrong, and people can correct me next week if they go and look it up. But why is it that iron and nickel have the lowest binding energy? Why is it that the particular arrangement of protons and neutrons in iron have this property that they don't, that when you add stuff onto them, you can't get energy out, whereas the lighter ones have that property? That's like a mystery of the universe, that particular arrangement of protons and neutrons is at the lowest energy. But that is just the way iron happens to behave, and that is just one link in the chain. If the elements are all hot enough, they will turn into heavier elements, and eventually they'll turn into heavier and heavier elements as I described. And that's just a link in. Those are just steps that nature allows it. And if you dump energy into the system, you'll get more heavier elements, and then you'll get iron. And then another process of nature has to take over to balance all the forces, and in the end, you end up with a neutron star. And so the neutron star it just happens to be an emergent property of nature. And I don't know if it has universal significance or significance to the universe. It just happens to be an emergent phenomenon of nature.
Let me get the last one.
Yes, please.
The proton in the star, the protons, they collide. When they collide, they give a lot of energy. But we see that in the LHC, the condition that happen in the LHC, that protons, they speed up the protons, they collide, and they give a very important particle called Higgs boson, that gives all the particle mass. Does that take place also in the sun? The proton collide in the sun.
So I don't believe that the center of mass energy. So you have to give one proton a lot of energy in the LHC, and you give another proton a lot of energy, and so you dump a lot of energy through these two protons into a place that isn't moving, because the relative motion of the one proton and the relative motion of the other proton cancels out, and so you end up dumping a lot of energy into one place that does not have motion. So you're dumping a lot of energy into one particular place in space, and then you can get, like you said, you can generate a myriad of particles, including now we believe the Higgs boson. But I don't believe that the energies that are required for that are happening in the sun. I mean, the sun, at the end of the day, the sun is the thing that gives us the energy to, to actually make nuclear power stations and make solar stations that give us the electricity that we'd send to the guys at CERN, and the guys turn all that energy and then make it. So at the end of the day, the sun is providing the energy that's used in the LHC. So the energy source in the sun is there, but the configuration of dumping that energy into two protons and colliding them together, I don't think the sun distributes the energy in that way. So I think the sun has the energy source to certainly create the sort of stuff that CERN creates. But it doesn't, nature chooses not. We have to do a whole lot of work to make energy go in that way. And the sun can't be bothered with that. It's distributing the energy the most efficient way it can. Building the LHC is not very efficient. So yeah, I think the energy is there, but the sun doesn't do it.
The last question.
Okay, this is the last question then.
What happens when all the hydrogen atoms are consumed in the nuclear reaction that takes place in the sun? Would that affect our photosynthesis, the photosynthesis?
No, so by the time the Earth evolves, by the time the sun evolves to have burned up all its hydrogen, the processes of the red giant phase will have killed everything on the Earth. So there will be nothing on the Earth to photosynthesize. But if there was another planet, let's say we all figure it out and we pack up and we move to a planet on a more distant orbit that's further away from our now more sort of luminous star. So the red giant is a more luminous star, and we move on to a spaceship, or we move on to a planet that's further away. So now we're in the habitable zone of this red giant. Then would that affect photosynthesis? The color of the sun would be different, and plants that we have and that have evolved on the Earth have evolved a particular sensitivity to certain colors of light. So I would say that photosynthesis won't be interrupted, but maybe it won't be as good because the color spectrum of our red giant won't be the same as the color spectrum of our sun, and the plants on the Earth have evolved to work best with sunlight. So I would say it will affect photosynthesis, but probably not that much, and certainly not on the Earth because we'll all be gone. And with that, I thank you all. And